We just kind of went over the fact that we can make these power functions wider or narrower based on the magnitude of a, right? That number in front of the x to the certain power. And we also went over how these graphs can go in opposite directions from what we would expect based on the even or odd exponent by the negative sign in front of that power function if the value of a is negative. So we're going to look at a couple of multiple choice questions that kind of go off that. So I'm just going to draw a little picture over here. It says if 6, -2 lies on the graph of a power function. So 6, -2 is pretty far out here, but we know just by changing the value of a that we can get our power function to get wider. So not really a problem. It says this is a power function, so I know that this is going to have to go through the origin, right? That's always true, so I'm just going to draw that part of the graph. Now, then it says circle the point that would also lie in the graph if the exponent was even. So if I do even, I know both arrows have to go in the same direction, right? So this one would have to go this way. It's also symmetric, right? We said even powered functions are symmetric over the y-axis. So if I have 6, -2, I have to have -6, -2 over here on this side. So that's what I'm going to circle. It says draw a box around the point that would lie on the graph if the exponent was odd. So remember, the blue is my initial piece I know has to be true. If it was odd, we know the arrows have to go in opposite directions. Okay. We also know that the graph has rotational symmetry of 180 about the origin, so this point could go with this point. This point is -6, +2. So that point is right here, and we're going to put a box around it. So that's just, whether or not the exponent is even or odd, we can know if the arrows go in the same direction or opposite, and we also use that symmetry rule to find other points. Exercise 7 says, which of the following power functions is shown in the graph below? Explain your choice. Do so without the use of a calculator. So first off, and you should really try this one on your own, but if you're just watching through, I look at this and the arrows are going in the same direction. So that means even exponent. So I'm going to cross out 1 and 4. Now both are going down, which means I have a negative lead coefficient. I have no idea what the window is. I don't really know how wide this is. Like, none of this information is labeled for me, but I do know it's even exponent and negative lead coefficient. Now, I mentioned at the beginning of the video that a lot of our unit is going to be on these polynomial functions. That's the title of the unit. And this is our first time looking at a polynomial function. So we're also going to bring in some vocabulary, something called end behavior. The behavior of polynomials as the input variable gets very large, both positive and negative, is important to understand. So what does the graph do as I head towards the x's being either positive infinity, very positively large, or negative infinity in the negative direction? Now we're going to explore that in this exercise. This is your polynomial function. So a polynomial function is basically a bunch of power functions added or subtracted together. So we have x cubed, -2x squared, -29x, and then 30 if we say that the exponent could be 0. It's not really a power function, it's just a constant. It won't have too much impact on the graph. And we're going to compare that to this power function, right? That's a power function because it just has one term. The polynomial function can have more than one term. So this is an exercise that's really best done on a calculator. Basically, you're going to graph them with this viewing window, and when I graph them with that viewing window, I drew a little axes over here. My polynomial function, which I'm going to do in red, looks kind of like this. And my power function, which I'm going to do in black, looks like this. So we can see some similarities, but they definitely look like different graphs. Now, as I head in this direction and I keep making my window more zoomed out, finally when I get down to this one, basically the two graphs look the same. So I'm just going to draw this out. If we had that most zoomed out window, both of the graphs, so my polynomial function these, when we're so zoomed out, these loops kind of become insignificant and we don't see them. And we only see what's called the end behavior, or where the arrows are going. So they actually look like they're the same graph. So what do you observe about the nature of the two graphs as the viewing window gets larger? They look the same. Why is this occurring? So basically we will see, since a polynomial function is just kind of like a bunch of little power functions together and then maybe a constant, the one that ultimately wins out in the long run or in the end behavior is the one with the highest exponent. So basically, since x cubed has the largest exponent, the end behavior will model that power function. So if I chopped off the x cubed here, let's say I just crossed it out, this graph, while it would do some loops, would look like the power function negative 2x squared. Basically, whichever has the biggest exponent, if you zoom out enough and just think about where it goes in the end behavior, those arrows, it looks like that one. So here's a follow-up question. What power function best represents the end behavior of y equals negative 3x to the fourth plus 2x cubed minus x squared plus 5? So this one will also have some loops in it, kind of like we saw in the last one, but because the highest exponent is here, if I did end behavior, it would look like negative 3x to the fourth. Now, just thinking about that, if I use that zoomed out window or any zoomed out window that's super zoomed out, that means ultimately, even though there's some loops going on in the middle, even exponent, negative lead coefficient, it's going to look like that. So we're going to generalize that end behavior. It's a big, even though we're not really going to talk about power functions too much as we move on, they'll come up, in passing. We're going to be talking about those bigger, more termed polynomial functions. This is what dictates the end behavior. So here we have our general form of a power function, y equals a times x to the b. If b is even, so even exponent, and the a value is positive, here we're just going to graph what it looks like. So we know it's going to be something like this. It might be wider, it might be narrower, but that's the basic shape. So when we write end behavior, I'm going to star these off here as x goes to negative infinity. So this is the negative x direction. Where does y go? So this side is pointing up, so y goes to positive infinity. And this is how you write end behavior. We have like kind of a template on the first two, and then we'll have to write it ourselves on the bottom. In the other direction, which I'm going to do in blue, as x goes to positive infinity, right, this is where x is going to positive infinity, the y also goes to positive infinity. And this just reflects the fact that we know both arrows point up if it's an even exponent and the a value is positive. So looking at our next one, we have a times x to the b. Now we have an odd exponent, but we still have a is positive. That looks like our x cubed or x to the fifth graphs, right? And this says generalizations for power functions. Remember, this works for those polynomial functions too that have the loops in the middle. Their end behavior is still going to match if this is true about the term with the biggest exponent. So here in the negative direction, which we were doing in red, I should have done the graph in black. I'm just going to trace that because I want to do it as we go along. So if I look as x goes to negative infinity, right, as x goes in that direction, y also goes down. So y is also going to negative infinity because this one goes down, not up. In the positive direction, as x goes to positive infinity, right, that's this side, the y is also going to positive infinity. So that's end behavior for those two graphs. Moving down the page, and I would really suggest trying both of these. These are our situations where we have a negative lead coefficient. So the b is even, both arrows go in the same direction, a is negative, it's going to look like this. So to write out our end behavior, and as I said, please try this yourself, this direction, which we're going to do in red, right? So this direction, as x goes back, as x goes to negative infinity, y is going down, so y is also going to negative infinity. On this side, as x goes to positive infinity, right, as x is getting bigger, y is still going down to negative infinity. And my last generalization for these power functions, which as I said carries over to those polynomial functions we'll be doing, looks like this, right? B is odd and a is negative, so it goes in that direction. So writing out our end behavior in this direction, as x is going back to negative infinity, y is going up to positive infinity. And in this direction, as x is going forward to positive infinity, y is going down to negative infinity. So they're going in opposite directions in terms of how the x and y are increasing and decreasing this time.